Alright, hello. I'm going to start this video with where I left off in the last one. So we did this learning check where we were provided the rate law for a reaction that had reactants A and B. The rate was the rate constant K times the concentration of A squared times concentration of B. So we could tell from that rate law that the rate is second order with respect to A, first order with respect to B. And what happens when you increase the temperature, when you increase the concentration of A, that would increase by a rate of whatever that increase is. So we said tripled squared. So 3 to the power of 2. If something is first order, then if you double or triple its concentration, you would double or triple its rate, that reaction rate. Now in the next couple of slides, we're going to determine what this rate law is. So this rate law for different reactions based on concentration data at different experiments. So we could tell if we doubled B and the reaction rate doubled, the reaction rate doubled, then we could tell exactly that the reaction was first order with respect to B. So we're going to go through this, and these would be scenarios where you're not provided the rate law, you don't know what that rate law is, but you have concentration of different reactants at different times and the rate at those times. So we have a reaction with two reactants, A and B, some coefficients, and we can right away write this out where we know that the rate is the rate constant times the concentration of A to N, which is whatever the reaction order is with respect to A, times the concentration of B with whatever the reaction order is with respect to B. So using this experimental data here, we have different experiments and the initial rate with those experiments, we can determine the reaction order with respect to A, the reaction order with respect to B, and the rate constant. You need to know the reaction orders before you can calculate rate constant. So that's what we'll do. We'll calculate these reaction orders and then the rate constant. So to determine the reaction order with respect to any reagent, we have to find two sets of experimental data where the concentration of the reactant that we're interested in is the only thing that changes. So for A, we're looking for the reaction order with respect to A. In experiments 1 and 2, the concentration of A is doubled, the concentration of B stays the same. So any change in the initial rate of this reaction is a direct result of the concentration of A changing. So we can use experiments 1 and 2, and we'll find the ratios of these two experiments. We'll take the rate of 1 divided by the rate of 2, and that ratio will be equal to the equation. So rate constant times concentration of A at time, you know what, let's do 2 over 1. So rate 2 over 1, you could do it either way. This is how I have it in my notes, so just to avoid any mistakes in the video, I'm going to do 2 over 1. So this should be equal concentration of A to the power of N at time 2, that one there, times the concentration of B at time 2. And this is rate constant times the concentration of A to the power of N at time 1 times the concentration of B to the power of M at time 1. Well, the concentration of B is not changing when we go from experiment 1 to experiment 2. Oh, change the slide. All right. Pretend we're working on A here, and then we'll go back for B. So still work on your A slide. Okay, so we're working with experiment 1 and 2. The concentration of B is not changing. It's 0.0250 in both, so we can cancel those out. They're not changing. K is also not changing, so we can cancel that out. So rate 2 over rate 1 is equal to the concentration of A at time 2 to the power of n divided by the concentration of A at time 1 to the power of n. We're looking at the ratio of these rates, which again is directly related to the ratio of the concentrations. We can simplify this further since we're raising the numerator and the denominator to the power of n. We can bring that to the outside. Oh my gosh. N. Keep making mistakes here. Okay, so we can bring that to the outside of the fraction and put that fraction in parentheses, say the power to the n for both the numerator and the denominator. This is helpful for the next part. So getting to this, rate 2 over rate 1 equals concentration of A at time 2 divided by concentration of A at time 1, all of that raised to the power of n, which is the reaction order with respect to A. Now we'll plug in values. So rate 2 is 8.16 times 10 to the negative 3. Molarity per second. Rate 1 is 2.04 times 10 to the negative 3 molarity per second. This is equal to concentration of A for experiment 2, and this is 0.0500 molar divided by concentration of A for experiment 1, 0.0250 molar. All of this raised to the power of n. If you take the left side and divide, you will find that that left side is equal to 4. Inside the parentheses, you do that division, this is equal to 2. So we have 4 equals 2 to the power of n. Now we have to think about which exponent, when applied to the value 2, gives you 4. Well, 2 squared is 4. So n is equal to 2. And this tells us the reaction, Rxn, short for reaction, is second order with respect to WRT with respect to reagent A. So at this point we can say that the rate is equal to rate constant times the concentration of A squared times the concentration of B to the power of m. We still need to find that reaction order with respect to B. Now we do another calculation to find the reaction order with respect to B. When finding experiments to determine the reaction order with respect to B, we want to make sure that the concentration of B is the only thing changing. The concentration of A is not changing. So looking at the table, we can use experiments 2 and 3. Concentration of A remains at 0.05. Concentration of B starts at 0.025, and in experiment 3, it's 0.05. So we'll do the same process. We'll take the rate of experiment 3 divided by the rate of experiment 2. This is equal to, I'm going to simplify this here, concentration of B for experiment 3 divided by concentration of B in experiment 2, all of this raised to the power of m. We can go through the same process as this slide where we wrote out the full rate law. So rate 2 is equal to K times concentration for experiment 2 times concentration for experiment 2. Cancel out what is present in both the numerator and denominator here, and then we get this final fraction with the exponent n. So that's what I did. That's the process to get to this fraction here with the exponent m. You can certainly write that out to convince yourself that we can make that leap. Now we can plug in values. So the rate of experiment 3, 1.63 times 10 to the negative second molarity per second. And then rate 2, 8.16 times 10 to the negative third molarity per second. This is equal to concentration at experiment 3 divided by concentration at experiment 2 to the power of m. Simplifying both sides, the left side is equal to 2. The fraction on the right side is equal to 2, so power of m. Now we think which exponent raised 2 raised to which exponent would equal 2. That would be if m, that exponent, equals 1. So this tells us reaction is first order with respect to B. So now we can write out the rate law. Rate is equal to rate constant times the concentration of A squared. That was the previous calculation. We found it second order with respect to A, times the concentration of B to the first power, but we usually just don't write that one, so we would leave that blank. So this is our rate law. We've got the equation. Now we can use that to determine K, the rate constant. So let's rewrite out the rate equation. So we have the rate law. We can use any one of these experiments, 1, 2, 3, or 4, plug in concentration of A, concentration of B, and the rate, and then all we're left with is to solve for K. Let's rearrange this equation. So rate divided by concentration of A squared times concentration of B, this is equal to K. And then we can use values from any one row or one experiment. Let's do experiment 1. It shouldn't matter. You should be able to use any row and you'll get the same K value. So experiment 1, the rate is 2.04 times 10 to the negative third molarity per second. Concentration of A is 0.0250 squared. Don't forget to square it. Concentration of B is also 0.0250 molar. Let me get units in here for concentration of A. Now, if you have a habit of leaving out units, I highly, highly recommend that you definitely leave them in for these types of equations, because you need to consider how the units are in the fraction to find the units for K. The units for K can change depending on the order of the reaction. So all of this is equal to K. If we simplify the values on the right side, on the left side, this is 130.56. Now we have to think about units. We have molarity, the top, we have molarity cubed in the denominator. This right here gives us molarity squared, and then times another molarity, so that results in molarity cubed. I will use green for units. So we have molarity per second over molarity cubed. When you have a unit on the top and the bottom of a denominator of a fraction, the exponent will cancel out. You subtract one from the other. We have more molarity units on the bottom, cubed on the bottom, one on the top. So that means that we will have molarity squared on the bottom and no molarity at the top. That got canceled out. And then we also have that per second at the top, which we can move into the denominator. Another way to think about this, I'll do this in the top right corner. So if we have molarity per second divided by molarity cubed, this is equal to molarity times second to the negative first power times molarity to the negative third power. That negative, if you keep it in the numerator, like all of this would be over 1. So if you move anything in the denominator to the numerator, you raise it to a negative power. So now we can simplify. This is seconds to the negative first power times molarity to the negative second power over 1, or 1 over second squared, no, not second squared, 1 over second times molarity squared. These are equivalent. So back to our rate constant, 130.56 molarity to the negative second power times seconds, that is equal to K. So our rate is equal to 131, we'll change the number of significant digits. You can keep it the same. I'm not doing that for any specific reason, just to simplify. So the rate is 131 per molarity squared per second squared times the concentration of A squared times the concentration of B. And we got that whole equation based on these experimental data. I will start with this slide when we meet back in person on Wednesday. But these are example reaction orders and rate laws. So if you have a reaction order of 0, its units of K are meters per second. We just had an overall reaction order of 3. Second order with respect to A, first order with respect to B, that's a total reaction order of 3. And so we have we have molarity to the negative second power and seconds to the negative first power. All right, we'll do a real example when we get back to class in person on Wednesday.